Well, good morning. So what we are going to do today, we are going to go through the Heaviside operator and develop the tools necessary for solving various kinds of problems, time-dependent problems, which basically you will see are equivalent to solving differential equations in different ways. So we are going to develop that using the Heaviside operator. So to refresh everyone's memory, the Heaviside operator P was defined as the differentiation. And usually we are dealing with, in this case, with differentiation with respect to time, although it doesn't have to be differentiation with time in general. So when we show P, a lowercase p, we mean this. So and then we also we showed this last time, that also 1 over p is defined as the integral from negative infinity to t of the function, of a certain function. So what happens is that, and we saw that these two can be inverse functions. In other words, p of 1 over p of x, so you can think about it this way, although we will start dropping these brackets very soon, it will be equal to 1 over p of x, and it would be equal to x only if and only the function x of negative infinity, and I'm losing the notation here loosely, is 0. So if you have this condition, then these two functions will be inverses of each other, and the order doesn't matter of application, which kind of makes sense. It's in fact, differentiation and integration are inverse functions, essentially, if you define them correctly and use them correctly. So, and we saw examples of that, right? I mean, so for example, if you have, like, if I say what is 1 over p of, let's say, cosine of 5t u of t, right? So this is some function, and I'm asking what is the 1 over p of that, which basically means if you're in doubt, use the definition. 1 over p of that is the integral from negative infinity to t of cosine of 5t u of t dt. Right? That's the definition of it. Now, again, noticing that this is a u of t, this product is 0 for all t's smaller than 0, right? So all negative t's. Therefore, I can evaluate this integral only for those values. However, I have to be very careful. So I can write it as this, cosine of 5t dt, but I have to be careful because this can generate a function that would have non-zero values at negative t's. And that's why I need to, when I do this, I need to bring a u of t outside to make sure that it forces whatever functional form you have here to 0 for negative t's, right? So that jumps out and it stays there. And when you do this, what is the integral of this? What is the indefinite integral of cosine of 5t? Negative 1 over 1/5 of, so it's u of t, you can write as negative 1/5 of sine of 5t evaluated from 0 to t times u of t. I'm sorry? Why negative? Indeed, why negative? There's no negative, it's positive. So cosine, yes. Sine is, the derivative of sine is cosine. Sine goes to cosine goes to minus sine. Yes. So now, so that's for that, and then that function in this case is going to be 1/5. Since sine of 0 is 0, it's going to be 1/5 sine of 5t u of t. So that's an example, right? I mean, very simple, basic example. But okay, so let's keep this here for a second, and let's go back and develop something that's a very useful tool. And essentially, it's a way of using this operator to solve, as you will see, you can use it quite a lot and generalize it quite a lot, a tool to solve all the linear differential equations, homogeneous differential equations. So what are we going to do? We are going to start with actual circuit thing. So let's think about the circuit which we've seen before. So let's say you have an RC circuit. And what we are going to define, we are going to call it a low-pass operator. And we'll talk about this. Now, if you think about this, there is some source here, Vs of t. And let's say we are interested in the voltage, so let's call this voltage V of t. If this is the input, that's the output. There's another way to think about this, right, as a system. As an input x of t and an output y of t, where x of t is vs of t and y of t is v of t, right? So, and the system is kind of like doing whatever it's doing. Now, why did I call it a low pass? I mean, we haven't talked about this extensively yet, and we'll get to see this later on when we go forward. But why is it a low pass response? What do we mean by low pass? Low pass implies that, and we haven't talked about frequencies really, but implies that low frequencies go through it, but high frequencies do not. Or it passes the low frequencies better than high frequencies. Now, again, we'll discuss this a little bit more, quite a bit formally and in more detail later on. But now, if you look at it, can you think about what this voltage would be if this was changing very, very, very slowly, this voltage? It wouldn't change much. It was kind of very slowly, or if it was a DC. If it didn't change at all, what would this voltage be? If it was a constant, if it was like a battery here. If I put 2 volts here, what do I see here? The 2 volts, right? Because there will be no current flowing, there will be no voltage drop across here. These 2 voltages will be the same. So now, as I start changing this voltage, as I move it faster and faster, there will be some current across there will be some charge in the capacitor, charging and discharging, and some of the voltage starts dropping here, but there will be current flowing to do that, which basically means that there will be some of the voltage dropping across the resistor. So you will see less and less of it here. And if you think about it, at very high frequency, if I move it rapidly enough, most of that voltage will appear across the resistor, and very little across the capacitor. So you see, at low frequency, everything goes through. But as you change it faster and faster, less and less goes through. Again, we will do this is a very hand-wavy, intuitive way of thinking about it. We'll do it more formally later on. So let's say you want to think about this and say that, okay, it's a transfer function, and you want to find out what it is. So let's first write the equation describing this circuit. How do we do that? Well, it's a very, very simple form of essentially nodal analysis. You can write KCL at this node, right? If I write KCL at this node, the sum of these 2 currents has to be 0, right? So what is that first current in terms of V and Vs? Who's going to do that? This time, let's see, maybe starting from the middle row in the back, yes. In front of Rohan. Yeah, yes? Yes. So what is this current in terms of V, this current in terms of V and Vs? Well, what is the voltage across this resistor? No, not necessarily, right? What is the voltage on this node? If this is ground, what is the voltage on this node? V, right? We've made it V. What is the voltage across on this node? Vs. So what is the voltage difference across the resistor? V minus Vs, if you want to have the current going in this way, right? So it's going to be V of t minus Vs of t divided by R. That's that current. Now, what is this current? We talked about capacitors before. What's the relationship between the current and voltage of a capacitor? Q is CV. Therefore, the current, so if Q of a capacitor is C times V. Therefore, its current, what's the definition of the current? dq dt is going to be C, if it's a linear capacitor, dV dt, right? So what is this current then? C dV dt, right, equals 0. So that's the equation, right? So now if you want to write it in terms of a differential equation, how would you describe it? So let's say you divide both sides by C, and then what I'm going to have is that I'm going to have dV dt plus 1 over RC times V of t equals, and move this term to the other side, 1 over RC Vs of t. Okay? So now this describes it. So why did I write it this way? What do I have on the left-hand side? It's the variable the function that I'm trying to solve for. It's a differential equation, right? What do I have on the right-hand side? It's the stimulus, right? So if I want to think about it in this framework, I can write this as y prime plus some a y equals some x of t. And these are functions of t, of course. Right? We may drop the functionality of t quite frequently because it want to make it look simpler. So this is a very classic basic differential equation. And what is A in this case? Now, we defined this as the time constant. You remember this, right? This was the time constant of an RC circuit. So we showed it at tau 1 over RC. In this case, it's going to be 1 over A, or A is 1 over tau. Just a constant. A is a constant. So these are two different ways of showing it. One is more related to the physical parameters, and the other one is more purely mathematical form. The question is, how do we go about solving this if we wanted to solve this equation? Or before even we do that, can we represent this can we write this with the P operator, with the Heaviside operator? How do we write that? There's only one derivative here, right? It shouldn't be that difficult. So is it fair to say this is P operating on y plus A times y equals x? If I want it to be really formal, I should have done it this way. But I will drop it so you know what you're doing. We will keep dropping these things because we want to make things simple. So does this should make sense, right? This just means differentiate. Nothing fancy here, right? Make sense? Good. So now I can think of these two combined together as one operator, right? I mean, I can say, well, I can define this as P plus A operating on y, which means that differentiate and add the function with a constant of 8 multiplied by it. Right? This is that. It's notation. I'm just writing it this way. When I'm thinking about it as a whole as a single operator, I'm saying that there's an operator that it's a box that you give it a function, it takes the function and say, okay, let me take the derivative of this function, put it here, take the function, multiply it by a, put it here, add these two, and put it out. That's what that box does, that operator does. Right? Nothing special. So I'm showing that operator this way, which should make sense. Does it? All right. So now, if I think of this operator as an operator, I may have I want to have calculated the inverse operator. So I will define a notation. I'll come up with a notation for this, for the inverse operator. I'll show this inverse operator with this form. So at this point, this whole thing is a symbol. I'm just giving it a name. And I'm drawing, so this entire thing, which we'll call the low-pass operator, this is just, think of this as something. So think about it as some symbol, right, that I've drawn. I've just written it that way because it makes sense, as you will see later on, to write it that way. But for now, it's just a symbol. Think of it. So it's an operator that operates on x and generates y. Right? This is a useful thing, right? If I could find what this operator is, why is it useful? Because it solves a differential equation for me, right? Doesn't it? It takes the stimulus and produces the y. The purpose of solving a differential equation from a mathematical perspective is finding function y, right? From a physical perspective, it means that it takes the input and produces the output. So if I have a system and if I know its operator, if I throw in any arbitrary input here, if I know how to calculate this, I can calculate what the output is going to be for this particular function. Make sense? It's all time. So what we are going to do now is try to find out what this operator is. And we'll calculate it. And it's not that long a calculation. Just, it's probably we can finish it here. Let's see if we can fit it. So the first thing I'm going to do is a little bit of an arbitrary. It may sound a little bit arbitrary. But I'm going to calculate P of e to the at x of, y of t. Which is basically means the differentiation, the derivative of this thing, right? I'm going to differentiate this, right? Calculate the derivative of this thing. What is the derivative of this thing? So who's next in line? Yeah. That's it. The derivative of this function, this product of these two functions. A e to the at y of t plus e to the at y dash of t. E to the at y prime of t. Right? Y prime, yeah. Yeah, y prime, which I can write it as p of py. Does that make sense? Is it okay? Yeah. If I write it as py? Good. That's correct. Thank you. So now, we're good with this, right? So I can also rewrite this. So I can take the e to the at out, and I can write it as py plus ay, right? Which I can also, in my notation, I can write it as p plus a of y, operating on y, right? This is the same thing as this, right? Make sense? So I got that. Now, and I know from this side that from this equation that this is the case. So if I multiply both sides of this equation by e to the e to the at, what do I get? On the left-hand side, I get p plus a y e to the at, right? I'm taking this, multiplying both sides by e to the at, some constant, some function, not constant. And on the right side, I get e to the at. I multiply by this side of the equation. So I take this, and then, never mind, sorry. And then sorry, I'm making a confusion. I'm multiplying both sides of this by e to the at. I multiply this side of it by that. And the other side, I get e to the at x of t. Right? But from this expression, I know, so I have this guy, which is the same thing. Now my purpose was to make this side of equation look like that, right? And we succeeded in doing that, right? These two are the same. But from this first equation, I know that this whole thing is pe to the aty, right? So this is p of e to the at y of t. So I'm going to take a look at this and try to find y in terms of x. How do we want to find y in terms of x? So what do we need? We need to apply the inverses of these functions. So this is like an onion, right? Right? So I'm going to peeling this onion. So every layer I peel, I have to put the unpeeled, the opposite peel on the other side. Right? 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 Think about, so let's say this is the peel, one peel. This is the unpeel, or like this. So every time I take one layer off, I have to put the opposite of it on the other side. Or you can think about applying the opposite operator to both sides, if that makes you feel better, if my onion analogy doesn't help. I guess ogres were like that too, right? Anyway, so here's the thing. So what's the first step? What's the first thing I need to apply to both sides to get to the core of this thing, the y of t? 1 over p, right? The inverse of p. So I apply that. I say 1 over p. So I do 1 over p. And I'm going to reorder it. So I'm going to put this on this side and put that on that side. So I'm going to say 1 over p e to the at y of t. And on the other side, I will have 1 over p e to the at x of t. Right? So these two cancel each other, right? Subject to that condition that we discussed. So now the next thing I have to again unpeel one more time. So what's the inverse? I want to get rid of this e to the at. You can say I multiply by e to the negative at. You can say I divide by e to the at. You can say I unpeel the onion. Doesn't matter. It's the same thing. Or peel the onion, I guess, not unpeel. But anyway. So I multiply by e to the negative at. So now I found y in terms of x, right? For any arbitrary x. But by definition, this is this operator. Didn't we define this as this operator? So we know what this operator is. So what this operator, this low-pass operator operating on x of t, is e to the negative at 1 over p e to the at x of t. And this is an important result, worth remembering. So this operator that I defined, which is the inverse of the p plus a operator, is defined this way. It's a time domain function. Right? So you can actually, so this is called first order low pass operator. Quite important. So let's see what we can do with this. Let's apply it and see how it works. Is everyone good with this? I'm going to rewrite it down here too. So our first, the first order low pass operator is e to the negative at 1 over p e to the at x of t. You can also write this as an integral if that makes you feel better. You can replace this with the integral from negative infinity to t of this dt. Same thing, right? Everyone's good with this? All right, so let's see what we can do with it. So let's say I want to solve a differential equation. Let's say my differential equation is y prime plus ay, first order differential equals x. And let's say I want to solve it for x of t equals delta of t. So example 1. So we are trying to use this to solve this differential equation. Okay. What do we need to do? What is y of t? So we are trying to find y of t, right? Remember, here we basically have written p plus a of y equals x. These two are the same thing. So if I want to find y, what do I have to do? Apply the inverse operator of this inverse of this operator, which is what? Which we showed as 1 over p plus a. This is the symbol for the inverse of that. And apply it to x, where it's a delta of t. So what do I need to do? So who's next in line? Yes. So what I would need to apply this inverse operator to the inputs that I have, right? So in other words, I'm calculating 1 over p plus a of delta of t. So can you spell it out for me? E to the negative at times
1 over p.
Okay, let's write it as the integral. Okay. Because we need to evaluate it anyway. So tell me what the integral is.
Integral from negative infinity to t of e to the at times delta
of t dt. Right? This is an annoying nuisance that you have to do, generally speaking. I mean, you have to change this variable from that variable to differentiate, not differentiate, to separate them. I guess. If you don't want to use the word differentiate, to discriminate between them, I guess. Okay? So that's what is, are we done? Can you simplify this a little bit more? Considering the fact that it's the delta of t. There are good things about delta of t, right? So what can you say about the value of this function?
You can take that one out and make it 1.
1, exactly. You can take it out and make it 1. Why?
Because the area under it is 1, but only at one point, so it's going to be 1 wherever.
Okay, so the area is not coming into play yet. So the value of this function is 0 at all times other than t equals 0. So the value, so it's a 0 times some function. At all those functions, doesn't matter. So the value of this part of this product only matters at t equals 0. What is the value of this thing at t equals 0? 1, right? So this becomes 1. So now you're stuck with this thing. So you have e to the negative at integral from negative infinity to t of delta t prime dt. So what is this function? Or it's 1 over p of delta of t. No, this integral. Oh, yeah, oh, sure, yes. Yeah. Just the integral?
That's 1.
That's 1, are you sure?
0.
No.
Half.
It's both. It's both of them, depending on what time you're looking at. It could be either one. What is the integral of delta? We talked about this, right? From negative infinity to t. You remember?
No,
think about it, right? So if this is the delta, if I'm starting integrating, what's the area underneath this? Let's say I'm showing this area here. As I'm starting from negative infinity, the area is what? 0, 0, 0, 0, 0, 0. Once I get here to the delta, it just jumps up to what?
1.
1. So what's the integral of delta?
U
U of t, right? the same way that the derivative of u of t was delta of t, right? So p of u of t is delta of t, and 1 over p of delta of t is u of t. You remember this? Okay, good. So what is this?
It's u of t.
U of t. So e to the negative at u of t. So the impulse response of the system is this function. It's, so I'm going to show it here. The impulse response is this. Now, if you don't put that u of t there, it would be something very different. It would become like that, right? And that has several problems. What's the biggest problem with that? Go ahead. Okay, and what's the problem with that? Causality, right? I mean, so it produces an output before it has an input. Because the input came at t equals 0. It's the delta of t. Anything before that cannot be caused by that if it's causal, if it's causality. But anyway, so that's why these u of t's, make sure you don't drop them. There's sufficient number of errors caused by dropping these u of t's. So that's one example. So let's do another example with this equation. So example 2. Let's get rid of these. This is getting too crowded here. Example 2. So let's say my x of t is u of t. Let's do this one. Right? So x of t is u of t. I'm trying to find what my output is to a different input. So this time I'm making an input that's, instead of delta, is u of t. It's a step function. So I want to see what's the step response of the system, usually shown with s of t. So who's next in line? Let's go through it. Yes, go ahead.
So yt is, remember, p plus a.
E to the negative at, remember this expression, right? E to the negative at, you are applying this expression. Integral from negative infinity to t of e to the at u of t dt. Okay? And then how do we calculate this? We take advantage of this. We do something about it.
Taking integrals like u or 0 to t.
Exactly. So it becomes e to the negative at. I take this u of t, put it up front, so I don't forget about it, and I don't get confused about whether it's inside or outside the integral. So I put it in the front. If I put it back here, then I have to put like brackets and all those things. And just make sure that it's not inside the argument of the integral. Again, it's notational thing, just for simplicity. So then now the limits of integral change from what?
To
0 to t, exactly. E to the at prime dt prime, right? And this is an integral we should be able to calculate.
So 1 over a.
Okay, so 1 over a, I'll keep the stuff up front. So what do I have? E to the at evaluated from 0 to t, which is what? So I have 1 over a e to the negative at u of t, all the stuff I have to carry with me. Then what do I have here? For this, I get e to the at minus 1. Right. So e to the at minus 1. So now I can simplify it by multiplying this out. Just the product of these two is 1 over a, 1 minus e to the at, because this cancels that, becomes 1. And then this times that is e to the negative at u of t. So this is the step response of the system. If you look at it, you will see that it looks like this. It goes to 1 over a. Asymptotically, the time constant is 1 over a. And it's an exponential. So this is the asymptote. Okay? Does it make sense? And you can kind of see, right? I mean, just when I say low pass, again, we will develop this intuition more. And this time constant is also 1 over A. So you can see, for example, the step response. It kind of looks like a step, but it has taken away the sharp edges, the rough edges, right? I mean, the input was pretty sharp. It was just a solid step. But that sudden jump has now turned into a more gradual jump. So the things that were moving very quickly are smoothed out. They can't go through as fast. We put an impulse in there, and it kind of looks like an impulse that's stretched out, right? Now, the smaller the time constant is, right? The smaller the time constant is, the faster this happens. So if I have a smaller time constant, this would be like this. Even if it were smaller, it would look like that. You can see that it's gradually becoming more and more like an actual impulse when time constants are small, which means that essentially it's becoming like a unity transfer function. Or here, if you think about it, as you start reducing the time constant, it becomes more and more like that and gets closer and closer to the actual step. That's the cutoff frequency or bandwidth of a filter. So this is basically essentially the simplest filter you can make. This basically it's a low pass filter. It passes lower frequencies, again, roughly speaking right now, and it lets the high frequencies, it blocks the high frequencies or attenuates them at least. You should have a sense for frequency, right? This sudden jumps are things that are high frequency, right? The DCs are lower frequencies, slow varying parts are not affected. So at the end of the day, it gets to the same value, the correct value, the final value. It's the DC, you get the step eventually. Right? Any questions so far? Yes?
So is A just determined by what would be in the differential equation?
Yeah, I mean, it's coming from the differential equation, right? I mean, here, for example, A is 1 over RC. But, I mean, if it's an electrical circuit, I mean, it may be there are many, many different things that produce this differential equation, right? It's this, you can have an inductor. We'll do an example with an inductor a little bit later. Or it could be something else. It could be a mechanical system. This could be a mass spring, this is not a mass spring. This is a mass damper, or spring damper system. I mean, a mass damper is probably said. So you have a mass and some friction, right, system. This can be radioactive decay of a nucleus. And many, many different things are governed by this first order differential equation. So that's what I'm saying, the difference between math and physics. This is more physics, this is more math. Right? Yes?
Will 1 over A always correspond to the time constant then as well?
Which one?
1 over A.
1 over A in the first order differential equations, yes. Which is basically related to things like, which is called a time constant. You could call it half-life. There are different things that are related to each other, right? They're all same concept, same behavior seen in different systems. Which means it's essentially every time the rate of something depends on its value. The rate and its value are dependent. The rate of something happening depends on its value. Now, in radioactive decay, the number of things that will decay at any given point in time depends on how many of them you have left, right? So if you start off with a large number, then you have more of these things happening. The more time passes, you have just basically deplete them, start getting less and less of that. That's why you get this kind of behavior. So anytime you have that nature of this relaxation, it's also called relaxation process. There are like probably at least 10 different names for this thing in different literature. It's the same concept. If you think about it, there are really I would say about 18 to 20 novel concepts in engineering, at least. I mean, I would say at least engineering, probably even extended. There are 7 or 8, there are about 20 things that are repeated. I mean, all of these things are considered one thing, right? It's that core concept. Everything gets kind of same thing. So, yes?
Does this equation remain the same if, say, the resistor and the capacitor are in parallel?
Well, we can find out, right? We can find out. So the equation would maybe be different, right? But it would be still first order. Because you only have one energy storage element. We haven't talked about this yet. You have another way to think about it is that you have only one degree of freedom.
Okay.
If you wanted to, and what that means is that you can only define one initial condition. Right? If you tell me what the voltage across this capacitor is, you've defined the circuit. in the state of the circuit, right? That means, well, that's what we mean by first order. It means that it has 1 degree of freedom. And you will see it will have 1 natural frequency. You will have all of those things come together because of that. It's a first order equation, differential equation. Again, there are like 20 different names for the same thing. Any other questions? All right. Okay, so this is the low pass operator. Now, we'll develop also a let's keep this here. Let's go somewhere else. So we can also define a high pass operator. So let's start again with a circuit. So let's say if I wanted to start with a circuit with a high pass circuit. Can you help me construct it using the same 2 components? If I wanted to just like use the resistor and a capacitor and make a high pass. So I have a source, Vs of t, and I want the output voltage, V of t, to be now this time high passed. In other words, I don't want the low frequency stuff to go through, but I want the high frequency stuff to go through. Okay. So, yes?
Just swap the locations, like just measure the voltage across the resistor.
Measure the voltage across the resistor, or basically swap the voltage capacitor and resistor, right? If I want to draw it in the same format. What you said is exactly true, with one caveat, except for the fact that you need to be looking at the voltage across the resistor. Your ground would be at a different place. If you want to measure a voltage with respect to ground, then you need to switch them. Yeah. But you're right, the voltage across the resistor will have that behavior. So I can put the capacitor here and the resistor here. Right? And now what you have, you can see at low frequencies, at DC, what is this voltage? If this is not very low frequency or DC. This voltage is 0, right? Because there will be no current flowing through this guy. There will be no voltage drop here. So it stops the low frequencies. But as the frequency increases, more and more current goes through, so you have more and more voltage across the resistor. Does that make sense? Good? Yeah? All right. So what is the differential equation describing this? Now, you can define this current and that current and then show their sum to be 0, right? So what is this current? Who's next in line? I guess you are. So how do I define this current? How is this related to the voltage across the capacitor? Okay, C dV dt, but d of what dt? What is the voltage across the capacitor in terms of V and Vs? V minus Vs, right? So it's d of V of t minus Vs of t. That's this voltage minus that voltage, right? Plus, what is the other term? V of t over R, exactly. Equals 0. So this is the differential equation describing this. Which, if I divide both sides by C and then reorder, I can write as d dt, dv dt plus 1 over tau, which is tau, we say RC. V of t equals Vs of t over tau. Oh, I'm sorry, no, not these. 1 over tau, no 1 over tau. D just dd dt of d of Vs of t. Right? Good? Agreed? All right. So I can, if you wanted to write it in the form, in the mathematical notation, you can write as y prime plus ay equals x prime. Right? Or in the Heaviside operator notation is p plus a y equals px. So I can think of this as saying, okay, well, y is that operator 1 over p plus a applied to p of x. So one way to think about it is say, well, look, you know what? I don't care. It's a new function. It's just a derivative of whatever the input is. And then I apply that operator that we calculated, that inverse operator, low-pass operator, to this to calculate it. That's one way to think about it. Another way to think about it is that, okay, well, I can also think of this as a new operator, which will have a different symbol. So this is another alternative is I can say this is a new operator. operating on this. So we want to see what the properties of this operator are, and how do we calculate it. So let's go back and calculate what this basically looks like for a practical situation. So let's use this way of solving this problem. So let's say we say, okay, y is 1 over p plus a of p of x. So let's apply it. Let's apply it to see what we get. It's basically, by definition, from what we calculated before, it's going to be e to the negative at, right? I'm just applying the operator that we calculated before, right? 1 over p, which is basically integral from negative infinity to t, of e to the at x prime of t dt. Or you know what? I'm going to use tau this time because to leave no ambiguity with the prime, what it means. Something like that. Right? I'm just applying that operator that we calculated to this and using this expression. There shouldn't be anything unusual, right? If it doesn't make sense, what I'm doing should make sense every step of the way. If it doesn't, you should stop me now. Because then we're building upon these things. Okay, so how do I calculate this integral? Can I do something about this integral? What is x prime? X prime is really dx d tau, right? So I can integrate by part to simplify this. So how do I integrate by part? Well, say, well, this is v. You can say x is u. So what my integral will be is going to be e to the negative at v times u. So I get e to the at x of t minus, now I will have the integral from negative infinity to t of this times the x times d e to the a. So v was e to the a tau at, so dv would be a e to the at dt. So I can basically plug that in. I would get an a. I would get e to the at x of, or tau, because it's inside the integral, d tau. Right? Did I do everything right? All right. So now I will carry this thing around. Oh, you know what? I can multiply this first part out and simplify it so I don't carry a whole bunch of stuff around with me. What is this times that? Just the x of t, right? Because this cancels that part. So I would get x of t minus a e to the negative at from here, integral from negative infinity to t of e to the a tau x of tau d tau. So what is this, by the way? Do you recognize this? Yes. I see some of you pointing out to the other whiteboard, which basically, this is the low-pass operator. This is 1 over p plus a of x. So I can write this as x of t minus a times 1 over p plus a of x of t. From that definition, from that boxed expression. It's not a definition, it's really the value of that operator. Which I can rewrite now as, do you agree that I can define an operator 1, unity operator? What's the unity operator? You give it a function, it gives it back to you exactly as it was. So I can call it a unity operator. So I can write this whole thing as unity operator minus a 1 over p plus a. If I want to really do it correctly in terms of operators, it's that. But this is a constant, so I can bring it into the operator. It doesn't matter. I can define a new operator. And you can see that it's really behaving like this. So what I was calculating was really p over p plus a of x, right? Now p over p plus x of x really acts like, these really are acting like rational functions. So you can see it behaves like a rational function, because if you actually treated these as rational functions, if you treated this as like 1 minus a over p plus a algebraically, what you see is that if you do all, of course, this becomes p plus a. The common denominator would be p plus a minus a becomes p over p plus a. So you can see that these things look like fractions or rational functions. And we show that, at least in this case, this is really this, which is, if you think of these things as rational functions, it would be true. So that's the power of these things that allows you to deal with these things like rational functions. And we'll see more of those. Now, in general, if you have these two pieces, what you can do is that you can say, OK, if I have an operator, p plus a over p plus b, I can write it as p plus b minus b plus a divided by p plus b, which would mean that I can write it as 1 minus or plus a minus b over p plus b. Which means that any operator can be broken down into a low pass and a high pass, or a low pass and a unity. So what does that mean? So for example, if I say, what is the step response of this system? I can write it as the sum of two things. I can say, well, the step response is the step response of a system with a unity response. What is the step response of a unity system? What is the response of a system, the unity system, to a step? A step. So it would be the step. It's a unity response, right? Unity system, right? It's not very sophisticated. Plus whatever this is. And that's a low-pass response. We've already calculated that. So that looks like a something like that, which goes from 0 to the value of a minus b with a time constant of 1 over b. So the overall response is something that starts from 1 and it goes to 1 plus a minus b asymptotically with a time constant of 1 over b. So if I wanted to calculate, for example, something like this, you can think of it as those two things. Now, okay, so let's come back here. That is really what we need to do is that part, the high pass response that we talked about, that you see right now, is really the key to understanding why these things behave like rational functions. So if I basically put this back down here, you will see that this is the key. But now the key element of all of this is this. This is a very powerful tool, and we'll utilize it a lot. We'll get a lot out of that, as you will see. So what can we do? What are some of the things we can do with that? So let's see. You know what? Let me go somewhere else. So let's move on to this board. And you may say, OK, fine, but that solves a first order differential equation. Well, let's say you have a second order differential equation. Let's say you have d2 dy dt squared plus a dy over dt plus by equals x. Or in shorter form notation, y double prime plus a y prime plus b y equals x. How can I show this in the Heaviside format? Do you agree that this is p times p operating on p, right? Or p squared. It's p operating twice. So this becomes p squared plus, what is this? Constant a times p plus the constant b. So this becomes an operator operating on y, generating x. Now, but in general, I should be able to factor something like this, right? I can factor it. This is what we call a character. If you think about these pieces as not operator, but actual algebraic variables, what happens is that you can actually factor this by fundamental theorem of algebra. So you can actually factor it, and you can say if I factor it, I can write it like this. I can write it as p plus a operating on p plus b y, where a plus b is capital A and a times b is capital B. So look at this and see if it actually does produce what you are looking for. So if I do it in this order, what do I get? First, this operates on this, so I get p plus a operating on py plus by. And then this operates on that. What do I get? I get p squared y. This operates on that. I get plus b py. This operates on that, which is basically a multiplication because it's a constant. A py plus this times that, which is just a by. So if you look at these two and combine them, you really do get p squared y plus a p, considering that a plus b is capital A, and then y, and then you get b y. So you can see that this is really equal to that when it operates. And you can change the order of these things, and you will still get the same thing. You could argue that by symmetry, because I just need to change the name of these things, and you will get the same thing, because these two expressions are symmetrical with respect to a and b. You can verify it yourself, right? So this is the useful part, right? So if I write it this way, so I can write this differential equation in this form, p plus a times p plus b, or operating on p plus b, y equals x. So if I give you something like that, can you solve this differential? How do you find y? Using the tool that we've already developed. We have the inverse low-pass operator. So how do we do that? Yeah.
1 over p plus b, 1 over p plus a x.
Yeah, and the order doesn't matter because the order of these things don't matter, right? So you can say y is 1 over p plus a, 1 over p plus b of x. What we really mean is this, right? But we are dropping those. So the operator, first this operator operates, and then this operator operates. But the order, since the order doesn't matter, you can apply them in any order you want, whatever is more convenient to you. So I can solve a second order differential equation that way. And let's do an example. I don't know, just like something simple. So let's say, example. Let's say y double prime plus 3y plus 2y prime plus 2y is x. And let's say x is, you can pick anything you want. Just like, e to the negative. Let's start with something simple, then we'll do more complex ones. U of t. Or even start with delta of t, and then we'll go to u of t. So let's find its impulse response first. Let's start with that. So we want to find y of t for x of t being delta of t. How do we do that? Well, first we have to look at the characteristic polynomial, right? The characteristic polynomial of this thing, which is this thing, is p squared plus 3p plus 2. So what are the roots of this thing? Minus 1 and minus 2, right? So you can write this as p plus 1 times p, or p plus 1 and p plus 2. So what I need to apply is really, so y of t, and see everything is in time domain here, is 1 over p plus 2 times 1 over p plus 1 of delta of t. So if I were a mathematician, I would declare victory at this point. I would just say, yeah, the problem is solved. But we are engineers. We have to find the answer. And it has to be correct. OK, so here's the thing. So how do I go about doing this? Who's next in line? Yes. Yes. Shweta. Shweta. Yeah, sorry. OK, go ahead. So which one do I need to calculate first? Right, this thing. So let's calculate it. So we keep this here. And then what is that? Express it in terms of that operator, right? That boxed result. e to the negative t, because a is 1. And then, okay, 1 over p. You can write as 1 over p, or you can write as the integral. I mean, eventually I would like you to start thinking as 1 over p, not write the integral every time. But for now, just till we get used to it, let's do it that. E to the t delta of t dt, right? So what is that? How do we calculate this integral? Is there a way to simplify it?
So we take out whatever value of t is at t equals 0, so that's just 1.
Right. So it only the value of this function only matters at t equals 0, where it's 1, because it's 0. This function is 0 at all other times. It's a product of two things. So this basically becomes 1. So what is it left? What am I left with? What is this integral? The integral of delta of t. What is it? U of t, right? Because it's 0 if t is smaller than 0, and it becomes 1 once you get past 0. So this is simply u of t. So this becomes 1 over p plus 2 e to the negative t u of t. So now I have to calculate this thing. I have to calculate 1 over p plus 2 of that. So which is what? Why don't you continue? Again, apply that result again. Negative 2t this time, right? This is because it's p plus 2. Negative 2t? E to the, what's inside the integral? E to the positive plus. 2t, yeah. Okay, times, no, there's no Dirac delta anymore. Now the result of that first operation was e to the negative t u of t, right? So it becomes e to the negative t u of t. You have to apply it to the result of that second operation, right? First operation, sorry. So it's this. Well, this simplifies a little bit, right? What is this product? E to the t. So, and what is that integral? What can I do with the step? Right, I can take it out and change the bound. So I get e to the negative 2t. I take the u of t out. I get 0 to t e to the t dt. And this should be doable. Right? What is this integral? E to the t minus 1. You get e to the t for this, and you get minus 1 because it's the indefinite integral is the same function. So you get e to the negative 2t times e to the t minus 1 u of t, which is e to the negative t minus e to the negative 2t u of t. Actually, this is interesting. You remember we said when we talked about the impulse being that gigantic shock to the system that brings out all of its characteristic behavior and unnatural frequencies? You see, actually, you brought the two natural frequencies out. These are complex frequencies, and we'll see them later. So you see the two time constants of the system, 1 and the 2, or 1 and 1/2 essentially, really, right? Or the two natural frequencies of the system. When you hit it with the impulse, it produced both e to the negative t and e to the negative 2t. And again, we'll see more of this, and we'll do this more formally later on. But I want you to start seeing these things. Yes?
What would be like a physical equivalent to this if we had like a spring doing a mass to hitting?
This is a mass spring system. This is a mass spring and friction or damper system.
So like hitting that with an impulse would be like you're totally like kicking it upward.
You're kicking it very hard, but not just a very quick and brief kick. It's not a prolonged push. It's a jolt of the system, instantaneous.
In like physics right now, like what we're learning, would this be like analogous to normal modes? Or
These are related to normal modes directly. Yes, correct. Natural frequencies, normal modes, all of those are essentially the same thing again. These are, and you will see, we'll see later on, these are roots of the denominator of the transfer function, but we'll get to that later on. Yes.
What's preventing us from like splitting the 1 over p plus 2 and 1 over p plus 1 into like fractions that we can just add or subtract?
Nothing. We'll do that too. That's called partial fraction expansion. That's a very good observation. So she's asking, say, what is preventing us from breaking this into sum of 2 fractions, which would be something we'll do next lecture, next time. Yeah, or yeah, maybe 1 or 2 lectures. Yeah, that's actually a better and more generalizable way of doing this. You can write them as partial fraction expansions. And then once you write them as partial fraction expansions, you will basically use the superposition to just get the responses to individual parts, and then you can just add the individual responses together. Very good observation. Yes, absolutely, that's correct. Yes, Julie.
So if e to the negative t and e to the negative 2t correspond to p plus 1 and p plus 2, which are symmetric, why is one positive and one negative?
Oh, I see. Okay, so it really depends on the relative sizes of the response they produce. Because 1 over p plus 1 and 1 plus p plus 2 produce responses that are not exactly scaled, if you think. And by that, what I mean, okay, so let's look at this here. You see, for example, in the step response, you will see that there's a scaling of 1 over a. Right? And then in this one is also, what you see is that it's producing, the area of this thing is not constant as the time constant is going down. So if you want to get a really kind of like a normalized response, you have to have something that basically whose area gets normalized. So there's lack of normalization there. So one becomes larger than the other one, so one dominates the other one. But that's a good question. Good observation. Any other questions or observations or comments? Okay, so this was one example. So let's do a couple more with this. Just, I don't know, we can, I don't know, we can pick another one. Let's pick something a little bit more interesting. Let's try the same equation. So this is another example. And so let's say we do another equation, y double prime plus 3y prime plus 2y equals x. And we saw that basically y was, you could calculate as 1 over p plus 2, 1 over p plus 1, or in the opposite order of x. This time x is e to the negative t u of t. Right? So now kind of like considering what we said, we are really hitting it at one of its natural frequencies. You're hitting it, it's like a person being excited about the things that they're really excited to begin with. Say, yeah, you know, is this something that they have resonance on, right? Or something they resonate with, if you will. I mean, this is not exactly resonance in the classical sense, but you're hitting it at a complex frequency. And you will see, complex frequencies are more general form of what you know as frequencies, which are the frequencies of sines and cosines. So they subsume all of these exponentials and things of that sort. So I'm hitting it at one of these e to the negative 1, negative t. So let's see what happens. So I can apply them in any order. This time we can apply it in the opposite order. So let's say I do the calculation. I say y is 1 over p plus 1. Or, you know, let's keep it the same order. Whatever works better for you, right? Whatever makes your life easier. There's no point in making it more complex than it needs to be. So we are calculating this. So first we are calculating this part. So what is that? I'm just going to keep this here so that I don't forget about that. What is this part? Who's next? Yes. E to the negative t, right?
Yeah.
Right? Okay. From negative infinity to t of e to the t times. Yeah, that's why I started with this one. Because I'm lazy, I want to kind of go through get to the answer as fast as I can. because I knew that's going to cancel that. Okay, so this is good because these two cancel. So it's the integral. So what is this?
That's just u t.
So is that u of t? The integral, it's the integral of u of t.
All right, so it will be the
It's 1 over p of u of t. Think area, right? So if I try to calculate the area under this from negative infinity to here, 0, 0, 0, 0, 0, 0, what are you going to get? Ramp function, yeah, right. It's going to go up. So it's basically t u of t, or r of t. It's t u of t, right? So this produces what? This produces t u of t, right, times e to the negative t. Now, one of the interesting things that you see that this was the part that was responsible for that frequency. When I hit it with its own frequency, with its natural frequency, you see that I got a t e to the u of e to the negative t. So this is like, looks ugly. T e to the negative t u of t, right? So when you hit it at its natural frequency, then it gets this additional t to make it grow faster even, if you will. It gets more excited about it than it normally would. So normally you talk about, I don't know, something, they would start to talk about football, they start talking about, you know, guitar. You start talking about guitar, they get really excited. Say, oh, yeah. All right. Anyway, so what is the next? So we are not done yet, though, right? So what is the next step? What do we do next?
so that becomes
E to the negative 2t, integral from negative infinity to t, e to the 2t, times t times u of t. Yes, thank you, dt. So these two combined give me what? E to the t, right? So these two combined give me just e to the t. So I have to integrate this. I have to get integral, calculate the integral of from negative infinity to t of e to the t, t e to the t dt, u of t. So with the u of t I can basically take care of, right? What do I do with the u of t? I change the limit of integration and bring it out. So I make it from 0 to t and u of t, but I have to bring it out. I can't just kill it, right? So e to the negative 2t u of t is there. So now how do I calculate this integral? By parts, right? So just basically what you say, well, okay, this is du, this is v. So I get v du. In this case, it basically becomes t e to the negative e to the t minus integral from 0 to t of e to the t dt, which is what? So what is this? So the first part is t e to the t. What is this integral? 0 to t of e to the t dt. Minus e to the t minus 1, okay. Or I can write it as plus, or minus e to the t plus 1. Right. U of t. Don't forget the u of t. So, okay, so I can multiply this by those. So what do I get? I get t e to the negative t minus e to the negative t plus e to the negative 2t u of t, which you can also write if you want. I mean, I don't think it's fundamentally any better. You see, the part that I didn't hit, so it had two natural frequencies, right? Two things it really liked. I hit it with one. That thing had this additional t. It produced this t. It's kind of growing faster. It's getting more excited about it. The part that I didn't talk about, it still came out. But it didn't come out as strongly as the other one. Right? Does it make sense? So, but this is, you can see that this is a powerful tool, right? This allows you to solve differential equations without actually solving, I mean, you're solving them without actually doing some of the extra things. That expression is quite powerful. So let's take a quick break.